Welcome back to the series on statistics. Up until this point in the series, we've only really talked about probability and discrete probability distributions, when we're dealing with finite possible outcomes for a given statistical experiment. At this point in the series, we want to transition into talking about continuous probability distributions, where the possible outcomes of a given experiment can take on any of infinitely many values that exist over some interval. And we're going to talk more about precisely what that means in a moment, but for now, I have this little warm-up here because as we transition into this segment of the course, we're going to start using more and more elements from calculus. It's going to become necessary. Up until this point, I think the only element from calculus we've used is taking the limit when we derived the probability mass function for the Poisson distribution, but now we're going to have to start integrating more and maybe taking some derivatives, but not as many. Mostly we're going to be integrating. So with that said, let's get started here with this little warm-up. We're just asked to consider how you might calculate mass from a graph of density versus volume for a particular substance. So here we have our density on the y-axis, volume on the x-axis. And obviously the density here is going to be constant because it's an intrinsic property to a substance. And we have a density here of about 1,000 kilograms per meters cubed. So this is probably water or some kind of water-like substance that we're dealing with here. And if you wanted to calculate the mass, obviously you could just use the equation for density. This is like a 5th grade science problem. You just say that density is mass divided by volume. So mass would be density times volume. And if you wanted the mass of 1 meters cubed of water, you would just multiply the density in 1 meter cubed and you would get 1,000 kilograms. Very easy. But we want to consider this graphically because although this might be absurd if you're thinking about the density of a particular substance, just bear with me, suspend your disbelief for a second, and imagine a situation where the density was not constant, where the density was changing. And so the point that I want to make here is that the mass represented graphically here is just going to be the area under this curve. Right? And that should make sense. So we have a height here of 1,000 kilograms per meters cubed, and we have a width here of 1 meters cubed. So when you take the product of the width and the height of this rectangle, you're going to get the area under this curve, but the product of the volume and the density is going to give us the mass, which is what we intuitively should understand from the 5th grade science problem. And so the point here is that if we had a density function that was changing with respect to the volume, and so let's say we had some function here that represented the density. This is a density function. If we were to integrate over this density function over some interval with respect to the volume, we would get the mass. And so here, obviously, if you're integrating over the constant, it's the same as finding the area under the curve here. So this is just going to give us the mass of 1 meters cubed of water. But if our density was changing, we could solve for the mass by integrating over that density function. So that's the point I want to make here, just the connection I want to draw. All right, and that might seem very tangential, but I promise it's related. Let's do a little recap here of discrete distributions. These probability distributions dealt with situations where there were finite possible outcomes, as we said in the beginning. So we're talking about coin flips, dice rolls, any situation where there's only a discrete number of possible outcomes. So coin flip, you have heads or tails. Dice roll, you have integers 1 through 6 that you can land on, and there's no other possibilities there. And so in these situations, we had a probability mass function, which was a function that gave us the probability of a particular outcome occurring. And with these discrete distributions, we had this property that if you took the sum across all of the possible outcomes, if you evaluated their probability of occurring, and if you added up all of those probabilities, you would get a probability of 1, because if you're adding up the probabilities of every possible outcome occurring, well, something has to happen. You're adding up all of the possibilities, and so you're going to get a probability of 100%. And so let's think about how this might change as we move towards discrete or continuous distributions from discrete distributions, and we start considering statistical experiments that have infinitely many possible outcomes that exist over some range of values. And so with continuous distributions, there are infinitely many possible outcomes. And so let's talk about heights as an example. And so we're asked to consider what's the probability of being 6'2" or 5'11". I'm going to avoid that last question for now. And so let's just consider the first question here. What's the probability of being 6'2"? So the probability of your height equaling 6'2" is the exact same thing as saying the probability of your height equaling 74 inches, right? And so what is this probability? Let's think if we were statisticians and we went out and we wanted to figure this out. You could take a census data, I guess. Let's say we did census data and we talked to every single person in the United States and we asked them how tall they were. We could take all of the people that responded to that question on the census and said 6'2", and we could take that number of people, we could divide it by the United States population, and we could get some proportion of the population that identifies at 6'2", and that could tell us the probability of being 6'2" in the United States, for example. And now that sounds good, but let's just change that a little bit, and let's ask now what the probability is of your height being 74.0 inches. And now things change a little bit, because if you're, 6'2", if you're 74.1 inches tall, you're no longer included in this category. And so with this added bit of precision, we're getting rid of so many people that were previously included in that category. And so technically we could always just keep increasing this precision, right, down to the width of an atom. We could keep on adding zeros here, 0.000. We could just keep going forever. And you could imagine if you added infinitely many zeros, if you were to expected to carry out this experiment with an infinite amount of precision, down to the Planck length or something, just some ridiculously small number, and you're asked to find somebody who's exactly 6'2", exactly 74 inches tall. You can imagine that, but you're not going to find a single person who fits that criteria. There's only so many people, and if you are able to increase your restriction down to an infinite amount of precision, you can imagine you will never find somebody who meets those criteria. And so when we're dealing with continuous distributions, and we're asked, what is the probability of being 6'2", the probability of your height equal to 6'2", this is the situation where we're talking about. We're talking about an infinite precision. And so the probability of being 6'2" with infinite amount of precision is exactly the same as the probability of being 5'11", or 5'9", or 7'3", or 5'4", and the probability is 0. It is statistically impossible to be exactly that height. Now I know what you're thinking. You're thinking, Adam, I'm 6'2", I'm 5'11", I'm 5'9". These things can't be impossible. I know people that are these heights, and so they can't be impossible. And I hear you, but what's really going on here is, unless you're very insecure and you're rounding off to like that half or something like that, generally most people will round their height to a whole number integer. So most people are walking around saying they're 5'9", 5'7". They're not saying 5'9.839. That would be a very strange thing to do. And so when we're rounding our heights to these whole number integers, we're actually implying a range of values. So when we ask what's the probability of being 6'2", we're really asking what's the probability of being considered 6'2". And specifically what that means, if we're doing this, we're rounding to whole number integers, what we're asking is what's the probability of your height falling between 73.5 inclusive and 74.5 exclusive inches. That is the precise question that we're trying to answer here when we're saying what is your probability of being 6'2". That's actually what we mean. And so this actually does have a probability associated with it, because now we're not dealing with 74 inches down to the infinite amount of precision, 74.00000, all the way down to infinity inches tall, because obviously that is statistically impossible. But now we're talking about the sum of the probabilities of 74.00001, 0011, 0012. We're talking about summing up all of those probabilities. And so each of the probabilities for each of these particular outcomes is statistically impossible. It's effectively 0. But when we take the sum of these infinite amount of probabilities that exist between 73.5 and 74.5, there's infinitely many possibilities that exist between those two numbers. And when we take the sum of all of those infinitely many infinitesimal probabilities, we're going to get an actual number, an actual probability associated with your probability of being between 73.5 and 74.5 inches tall. And so when we're talking about this, when we're talking about summing up an infinite amount of infinitesimally small things, you might immediately jump to the idea of integration. And if that's where your mind is going, your intuition is correct. That's exactly where we're going with this. And so because of these problems with continuous data, where the probability of the outcome of a continuous random variable being equal to some particular outcome is always going to be equal to 0, it doesn't make sense to define a probability mass function for continuous distributions. And instead, it makes more sense to define what we call a probability density function, which is going to be a function, here I'm saying PDF, that exhibits the following property, where the probability of the outcome of our continuous random variable being between A and B is going to be given by the area under the probability density function from A to B. And so you might be asking, what is this probability density function going to look like? Well, that's going to depend on the statistical experiment that we're looking at the type of, or how the data is distributed. We're going to talk about different ways that this is going to look. But in general, every probability density function needs to exhibit this property to be a probability density function, that the area under it from A to B is going to give us the probability of the outcome of some continuous random variable from A to B. And it also needs to exhibit these properties. First of all, we should define a support. This is a set of all possible values that a random variable can take on. It doesn't need to be continuous, that's an error. But this is just a set of all possible outcomes for our continuous random variable, or our random variable. And so in this case, for a function f to be a valid probability density function of a continuous random variable x with support s, it has to also exhibit these properties. First of all, the probability density function has to be positive for all values of x in the support. You could think if the value was equal to 0, then that would just basically suggest that that possibility was, or that outcome was not possible. And so that's a contradiction, because then it wouldn't be contained in the support, which is the set of all possible outcomes. So it has to be greater than 0. You also can't have a negative probability density function, because probabilities can't be negative. So all of these, this function has to be positive for all values of x in our support. And second of all, is the property that we have to exhibit here is that if you integrate over all the possible values in the support, that's going to basically tell us the probability that the outcome of our statistical experiment is in the set of all possible outcomes of the statistical experiment. Well, that probability is going to have to equal 1. And so a valid probability density function has to exhibit these properties. It has to be positive for all the values in the support. If you integrate over the support, you have to get a value of 1. And also it has to exhibit this property up here. This is just the definition, where the area under the probability density function from A to B is going to give us the probability of the outcome of our continuous random variable being between A and B. So these are probability density functions, and this is going to be how we will negotiate continuous distributions. And for our first continuous probability distribution, it makes sense to talk about probably the simplest case that could possibly exist for a continuous distribution. Let's kind of get some practice in understanding these continuous probability distributions. And so the simplest case I could think of is the uniform distribution, where the probability of a random variable x taking on any value in its support is equal. And so that's why they would call it uniformly distributed. And so we want to see if we can identify some properties of a uniform distribution. And so here we say let x be a continuous random variable such that, and then this notation here means that x is uniformly distributed from A to B. That's what this means. Or x is a continuous random variable that is uniformly distributed from A to B. They're the same thing. And so we're asked to determine what the probability density function for this distribution is, as well as the mean and variance. And so how might we go about figuring out what this probability density function is? Well, there are some properties that we know. For example, we know that if we integrate the PDF with respect to x from A to B, from all the values in the support, we know that this has to equal 1. I'm going to clean this up a little bit. But we also know that the probability is constant everywhere. And so if the probability is constant everywhere, that just means it's going to be some constant number. We can just set that equal to a constant. And so this is going to become, we're integrating from A to B over C, which is some constant with respect to x. And we know that this is equal to 1. Now this becomes a very easy thing to evaluate. This is just going to be c times x evaluated at a to b is equal to 1. And that's just saying c times b minus a is equal to 1. And here we can solve pretty easily for c here. And we just get that c is 1 over b minus a. But c is just our probability density function. So we find that the probability density function is just going to be equal to 1 over b minus a. So for a uniform distribution, we know that the probability density function is just 1 over b minus a, where b and a are the bounds of the support for our uniform distribution. All right, so that's our PDF figured out for a uniform distribution. Let's see if we can figure out what the mean is. So let's make some space here. What's the mean of a uniform distribution? For this, it's probably going to be useful to recall that the mean for a discrete probability distribution was determined by summing up the products of the values of each outcome with the probabilities of those possible outcomes. And so for every possible outcome in that discrete distribution, we took the product of the probability of it occurring with its actual value, and we summed all of those together to get our mean. And so here, to apply the same logic, we need to sum up the product of x with the probability of x occurring for all x in the support. And because we're dealing with continuous data here, that means we're going to have to integrate. So here, our mean is going to be given by the definite integral from a to b, all the values in the support of x multiplied by the probability density function. So here, say, where f is the probability density function. And we can figure this out because now we know what the probability density function is. And so if we wanted to figure this out, we'd say that the mean is going to equal the integral from a to b of x over b minus a with respect to x. But this is just constant, so we can pull this out. This is just going to be 1 over b minus a times the integral of x from a to b with respect to x, and that's just x squared evaluated at b minus x squared evaluated at a. And so this is going to be, I'm going to factor out that 2, and this will be multiplied by b squared minus a squared. But here, this is just a difference of 2 squares, so we could reduce this further. Be 1 over 2 times b minus a times b plus a times b minus a. And these now cancel, and we're left with our mean is going to be equal to b plus a over 2. b plus a over 2. And so we get our mean of our uniform distribution is just b plus a over 2, where b and a are bounds of the support. Now it's worth pointing out here that if you know that your experiment is uniformly distributed, that the possible outcomes of your experiment are always equal over some interval, then you might expect that most of the time the outcome is going to hover somewhere around the middle of the interval, because those points where it winds up being towards the left half of the interval are going to cancel out with those where it winds up being towards the right end of the interval. And in general, on average, you're going to expect it to fall right at the midpoint of the interval. And that's exactly what we've computed here. You could think if our interval ran from 1 to 3, then b plus a over 2 would be 1 plus 3 over 2, which is just 2, and that's exactly the midpoint of the interval. So this should follow with our intuition quite nicely. All right, so now let's see if we could compute our variance here. We should remember that from our binomial and Poisson distribution videos, we know that the variance is going to be equal to the second moment minus the first moment squared. And so we just saw that if we're dealing with continuous data, then our first moment is going to be the integral over all of the values in support of that probability density function multiplied by the value in the support. And so you might expect that the second moment here is going to be exactly the same procedure, but instead of multiplying by x, we're going to be multiplying by x squared. It's very similar to what we were dealing with when we were dealing with continuous distributions. We just have to use integrals now because we're dealing with continuous data instead of just discrete sums. And so here this is going to be the definite integral from a to b of x squared times our probability density function. And our probability density function for the uniform distribution was just 1 over b minus a, as we saw in the beginning. So I'm just going to pull that out, knowing that that is a constant value. I'm going to pull it out of the integral. This is 1 over b minus a times the definite integral x squared from a to b. And then we're going to subtract the mean squared. And we already figured out what the mean was. And we saw that it was b plus a over 2. But we have to square it. And so I'm actually going to rewrite this as b plus a squared over 4. I think that looks a little bit nicer. So now we just need to contend with this integral here. And so this is just x cubed over 3 evaluated at b minus a. So this is going to be 1 over b minus a multiplied by b cubed minus a cubed over 3 minus b plus a squared over 4. So in order to move forward here, we have to factor out this expression right here. And you probably don't have the difference of cubes memorized. I know I didn't. But what this is actually going to reduce to is this is going to be 1 over b minus a. And then the b cubed minus a cubed can be factored out into b squared plus ab plus a squared times b minus a. If you don't believe me, I encourage you to FOIL this out and see that it does evaluate to b cubed minus a cubed. This is going to be divided by 3 minus b plus a squared over 4. And then here, this b minus a will cancel with that b minus a. And then what else can we do here? B squared plus ab plus a squared. Let's unfoil this so we can combine like terms here. And also let's try to get a common factor here, or common denominator here, so that we can actually simplify this a little bit. So this expression right here, this is going to be equal to 3 times b squared plus 2ab plus a squared over 12. Just this part here. And then this part is going to be equal to 4 times b squared plus ab plus a squared over 12. And so we have 4 times this, and then I'm going to stretch this out here, minus 3 times b squared plus 2ab plus a squared. And so that's going to be this expression simplified a little bit. Let's continue this simplification. And so here we're going to get 4b squared minus 3b squared. So that's just b squared. We have 4ab minus 3 times 2 minus 6ab. So 4 minus 6 is minus 2ab. Then we have 4a squared minus 3a squared. So that's going to be plus a squared. All of this over 12. And what does this evaluate to? Well, this is just b minus a squared. And so this is just b minus a squared over 12. And this is going to be our variance right here. And so what does this tell us? This tells us that the standard deviation of a uniform distribution is going to be the square root of b minus a squared over 12. This is our standard deviation here. And we know that our mean for a uniform distribution is b plus a over 2. Showed that in the beginning. And our probability density function is going to be equal to 1 over b minus a. And so we've shown that a uniform distribution will have all of these properties. All right, so now that we've established all these properties of a uniform distribution, our first continuous probability distribution, let's look at this example problem. I got this from the Statistics LibreText online textbook. I tried to come up with my own example, but I like to use examples that are actually applicable to real life, and the only time that the uniform distribution tends to crop up actually in real life is when you're dealing with quantization error, which got pretty complicated pretty fast. So this does have real-life applications, but they're not very easy to explain in a simple problem. So this is just going to be fine. We'll just use this example from this textbook, which is an approximation. Here we're told that we gathered data for the number of passengers on 35 different charter fishing boats, and the data followed a uniform distribution where all values between and including 0 and 14 are equally likely. Whereas to state the values of A and B, write the distribution in proper notation, and calculate the theoretical mean and standard deviation. So the reason this isn't actually a uniform distribution is because this is actually discrete data. You can't have a fraction of a person. And so when they say all the values between 0 and 14 are equally likely, that's not actually true. It's all of the integers between 0 and 14 are equally likely. But we're going to assume that this actually could be represented continuously, and that you could have a fraction of a person, just for the sake of practice. And so if we're asked to take the values of A and B are the bounds of the support, so the ends of the set of all possible outcomes. And so we said that all values between and including 0 and 14 are equally likely, so these are the bounds. So A here would be 0 and B would be 14. And if we wanted to write this in proper notation, we want to say that x is going to be a uniformly distributed random variable from 0 to 14. That's the way you would notate this formally. And now we want to calculate the theoretical mean and standard deviation. We just saw how to do that. Our mean is going to be b plus a over 2, which in this case is 14 plus 0 over 2, which is 7. And our standard deviation is going to be the square root of the variance, which is equal to the square root of, let's see, b minus a squared, that's 14 minus 0 squared, divided by 12. And so this is going to be 14 over the square root of 12. And so what's the square root of 12? We can factor out a 4 there. And so this is going to be 14 root 3 over, let's see, this would become 2 root 3. And so I'm going to change this 14 to a 7. This is going to become 7 root 3 over 3. Right, did I do that right? Yeah. And so this is going to be our standard deviation here. All right, so I hope that was an illuminating introduction to continuous probability distributions. I hope it wasn't too overwhelming. This is actually where statistics immediately starts to become applicable, because in the next video, we're going to start talking about the normal distribution, which has shockingly wide-reaching implications in every single field of study. It is incredible how this one distribution, which we're going to talk about in the next video, seems to fit so many wide, disparate sources of data. And so we're already on track here to start talking about very, very, very useful things. So I hope that's somewhat exciting. I hope you guys enjoyed. I'll see you guys in the next video.